According to the ancient Greeks, this would not be considered a beautiful rectangle. This is ugly. If we change the dimensions a bit, we can clearly see this is the most beautiful rectangle. If we turned it sideways, a pleasant human face would fit in it perfectly. This rectangle has the property that a plus b over a is the same as a over b. This ratio is approximately 1.61 to 1 and is called the golden ratio. Now, this segment up here is called the golden segment, and this is the golden rectangle. We find that the golden ratio can be written in this form here as a continuous fraction, or we could write it in this form here as a continued square root, both of which reduce to 1 plus the square root of 5 over 2, or approximately 1.618. Now, the golden ratio is found all over the place in geometry, art, architecture, and nature. Let's take a look at this. We start with a point, and we make 5 circles around this point that are spaced evenly about it, like this. And then we look at the intersections formed. We find that those points of intersection touch the unit circle, found here in pink, when the radii of the surrounding circles are equal to the golden ratio. This beautiful pentagon formed here, and the radius is equal to the golden ratio. Now, let's look at this regular pentagon here. It has sides of length 1. The segment AC, or any diagonal for that matter, has a length that is equal to the golden ratio. Moreover, if we connect the vertices of the pentagon, we get this beautiful star here. Now, let's look at this red segment right here. Let's take a look at its length. Is 0.618 centimeters. But if we take its reciprocal, we find that, lo and behold, we get, you guessed it, the golden ratio. Okay, now let's look at any regular pentagon. If we take a look at the ratio between its diagonal and its side, and this is for any size pentagon, we find that the ratio is the golden ratio. Very strange indeed. All right, now check this out. We're going to take a look at the Fibonacci sequence. It's formed by adding the previous 2 numbers to get the next number. For example, 2 is equal to 1 plus 1, 3 is equal to 2 plus 1, 5 is equal to 3 plus 2, 8 is equal to 5 plus 3, and so on. If we create a 1 by 1 square, and then we put another square on that, which is also 1 by 1. Oh, hold on there. And then we look at the ratio between the long side and the short side. We get 1 plus 1 over 1, or 2. Now, if we add on the long side another square, this time of length 2 by 2, and we take the ratio between the long side and the short side. We get, we take the long side divided by the short side. We get 1 plus 2 over 2, which is 1.5. Alright, now we'll add another square onto the long side, which is 3 by 3. Now if we take the ratio of the long side by the short side, we get 2 plus 3 over 3, or 1.67. Now we're going to continue with this process. We're going to add a 5 by 5 square. Okay, let's see what we have here. We have, this is 1 by 1. This is 1 by 1. This is 2 by 2. This is 3 by 3. And this is 5 by 5. Now we're going to take the ratio of the long side by the short side, and we get 3 plus 5 over 5, which is 1.60. Now we'll add on the 8 by 8 square. And again, we'll take the ratio of the long side by the short side. This time we get 5 plus 8 over 8, which is 1.63. We could carry this on, but I'm running out of space. Now the next one would be 13 by 13. And we find that its ratio would be 8 plus 13 over 13, which is 1.62. Now notice, we're getting closer and closer to the golden ratio. In fact, if we kept this up infinitely, the limit would be the golden ratio. Now, we can create this, this spiral here. We take this point and we make an arc through these points. And then we take this point and make an arc through these points. We take this point and make an arc through these points. And we take this point and we make an arc through these points, and so on. We get this beautiful spiral here. This spiral is found in various places in nature. We can find it here in spiral galaxies. And we can find it here in this lovely shell. As a matter of fact, the golden ratio and the golden spiral are found all over in nature. And it seems that this ratio has been known for over 5,000 years. If we take a look at the Great Pyramid here, which was made in about 3500 BC, and we divide that length by that length, we get a number extremely close to the golden ratio. It's in fact 1.618. As close to the golden ratio as you could possibly imagine in a structure this old and this large. My question is, why is the golden ratio found all over the place? Well, many great thinkers from Plato to Kepler have found something mystical in this mysterious proportion.